In this section, we are going to maximize or minimize functions subject to restrictions. So there are different cases we may consider. One case will be to optimize, and by optimizing, we mean finding the maximum or the minimum. So let me write it down. So finding maximum, minimum of functions under certain restrictions of functions f with restrictions. Well, we're just going to concentrate on one restriction for each one of the problems. There are different kinds of cases. Let me start with a big one. So you could have f of x, y, z, just a function with 3 inputs with a restriction, some kind of g expression of x, y, z equaling a constant, k constant. So that's one scenario we could have where we have to optimize a fourth variable. Remember, x, y, and z will be, in this case, independent variables. And so f, being a function of 3 variables, will be the fourth variable. So we want to optimize a fourth variable under this restriction. I know this looks general. When we start with the examples, this will make more sense, but I just want to show the generality of this. So this is one case. Another case is that you have a function of only 2 variables. And we want to optimize this, finding the maximum or minimum of that, given the restriction in this way, some kind of other equation that gives a restriction. So first, I want to give you a general idea that we could have 3 variables or 2 variables. If you take the f into account, which we should, that really means 4 variables. So that's really 3. That would be z equals x, y. We want to optimize this z. So that is another scenario. And then I guess if we go down in dimensions, we could have a regular function f of x subject to g of x equals a constant. All right, so that, I guess we could go down this way, and then we can go up the other way. We could have a function of 4 variables. So I could have started up here, but now you know the progression. Here we go 1 variable, 2 variables, 3 variables. We could have 4 variables. Instead of squeezing it up here, I'm just going to write it down here. So I guess we could have f of, oftentimes once you have more than 3 variables, instead of using x, y, z, because at that point we're running out of the alphabet, we start using x again, x1, and we just differentiate them by putting indexes on them, x1, x2, x3, x4, subject to having those x's having a relationship among themselves. So x1, x2, x3, x4 equals some kind of constant. So again, this is a progression, 1 variable, 2 variables, 3 variables. Had I done this correctly, I shouldn't say correctly, in the same progression, going up the same way, this should be squeezed up here. But I want us to start with 3s because most of the time you're going to do those 2. It's going to be rare that we're going to be working in class with that restriction. Now, this one doesn't really make sense because what this is saying is, see, once you have a equation of x fixed to a constant, that means that x has possibly only a finite number of inputs, unless you have to have it. Yeah, this is going to give us only typically a finite number of points that we can plug in. So in that case, all you have to do is plug in. And this is almost like a silly example. This doesn't happen really. Because again, this restriction forces x to be fixed. There could be more than 1 value, but only a few values typically. And so all you have to do is plug into here I guess we can do a problem like that too, but that could be confusing. This is a little bit of a confusing problem. It makes more sense to have those two, and we're going to start with examples such as this one. I'm going to tell you the method as we go through the examples. Um, but well, actually, no. I'm gonna explain I'm gonna explain the method as we go through the examples. I'm gonna try to put pages on my sheets so I can refer back to them. That was page 1. So let's start with an example. Example 1. Let's say we want to optimize. All of these examples are going to be optimizing, which means finding the maximum or the minimum of a function. So the function we're going to work with is going to be labeled as f, and we're going to have 2 variables. And the function we want to optimize is simply x plus y, which is, whoops, not x plus y, x plus 2y. I want to be able to tell them apart. X plus 2y. This is a plane. If you write z equals x plus 2y, then we know we're going to have some plane going up in some direction. Yep. So we want to optimize this. We want to find the maximum. Now, finding the maximum doesn't make sense because this plane keeps going up in the same direction forever. So there's not going to be maximum. There's not going to be a plateau because this is just going up. However, if we write a restriction, so subject to, and let's say our restriction is x squared plus y squared equals 25, okay, which is a circle of radius 5, center at the origin. So that means we're going to have, so the inputs are here, down here somewhere. That's the floor. This is the output z. We want to maximize z, but we only want to work with these guys, with the elements on the circle, or on the border of the circle itself. Not inside of the circle, but just on the border. So that is a restriction. So what is the maximum? Now, if we project this up to the plane, we're going to end up with an ellipse. We're going to have a maximum and a minimum. That's very interesting. We're going to have a maximum and a minimum on this ellipse. That is the projection of this circle. So x squared plus y squared equals 25 are points here. Within those inputs that are on the circle, we want to maximize this output. So we want to find the point where that is going to happen. Now we're going to use Lagrange multipliers, which implies we're going to use vectors. On the plane, if you find the gradient of this function, we're going to end up with the direction of maximum rise, the direction in which the graph is going up the fastest. So whatever direction it is, the vectors, the gradient are always going to go in the same direction. They're going to go up like this, up, up. They're going to be everywhere, you know. Or you can, yeah. And they're going to be all parallel, all of the same length. They're going to go up. Yep. Because that is the direction of maximum height. What we're going to do in this method, by the way, is form a new function. Form a new function. Typically, we're going to label it as g of x, y. And all we're going to do is take this equation, make it equal to 0, and put it in here. So we're going to end up with x squared plus y squared minus 25. There we go. If you did 25 minus x squared minus y squared, the method will work. So either put the 25 on the other side of the equation or put the x squared plus y squared on the other side of the equation. Whichever one of the two you do, the method will work. So we don't have to worry about that. Now, so by doing this, we are actually forming a paraboloid, all right? Because this is a paraboloid, it's shifted down by 25 units. And if we find the gradient of G, we're going to be finding the vectors that get away, well, the vectors of fastest increase of G. Now, G is increasing up in the direction away from the center. It's probably easier to do a top view of what's going on. Okay, so we have the plane. Now, this is an inclined plane. It's not flat. It's not horizontal. It is flat, but it's not horizontal. It is inclined. So this is at an angle. I'm drawing it from the top, so it looks like it's flat, but it isn't. Okay, and then we have this circle. Okay, so there's going to be a maximum. So from the top, the circle looks like a circle, but on the projection of the inclined plane, it will be an ellipse. So we're going to have, yeah, that is an interesting situation. Whenever you have a circle, I got my circle here. It is a circle, but if you look at it from the side, what you actually see is an ellipse. See, what we see right now is an ellipse, even though from this angle, it is a circle. So every time you tilt a circle, you get an ellipse. And that is what's going on here. We are, by projecting this circle onto the inclined plane, we're getting an ellipse. But it is still a circle from the top view. So this is the top view. We still see the circle. Yeah, this is an optic illusion. But in reality, we have and the opposite is true too. If you start with an ellipse, you can turn the ellipse until you actually get a circle. So it works both ways. That's kind of really, really weird. And most of us don't have a perfect ellipse around so that we can actually show by tilting it, you actually get a circle back. Anyway, so we have level curves. So this is 25. This level is going to be, if this is, no, this is going to be 0 rather. If x squared plus y squared equals 25, when we subtract 25, we get 0. So this is the level curve of 0. And then we have negative, 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 positive, positive, positive. And the gradient tells you the direction of increase, of highest increase. And because the next circle will be the next circle up, there's no next circle, but if there was a next circle up, then we would increase exactly away from the center of the circle. So these little vectors I'm drawing are the vectors of highest increase. And they don't have to be symmetric. The only thing that is important is that they have to be away from the center, in this case. All right. These vectors we drew are going in one direction. Up, whatever up is, that is the direction of those vectors on the plane. All of those are supposed to be going up in one direction. Maybe they're a little tilted, but they're supposed to be vertical. Anyway, so when is this vector going up matching this vector as far as being parallel? They may be of different lengths, but when those vectors going up match this one, that's when we find the maximum. Yep. Because here the vectors are going to be going out. They're gonna look like eyelashes going out the way. But where they match this vector, that's when we have the maximum. And when they match the opposite of this vector, they have the minimum. Before starting up this, we don't necessarily want to see or analyze where the function increases or where the function decreases. So when we are finding those 2 points, we do not necessarily know where the maximum and the minimum are. In this case, because this is pretty obvious that it is going to increase as you go away, the gradient that makes where those 2 vectors are parallel in the same direction is going to give us the maximum. But that is not necessarily the case. Uh, yeah, I don't want to elaborate too much on that because in practice, all we have to do is plug in numbers, and then it is going to be clear which one the maximum is and which one the minimum is after we plug in numbers. Anyway, so this is the idea. This is the method. Find the gradient of f. So there's f. The gradient is very simple. The derivative of this with respect to x will be 1. The derivative of the same whole thing with respect to y will be 2. Find the gradient of g. The gradient of g will be the derivative of this with respect to x, 2x. The derivative of that with respect to y, 2y. And that's it. And then we're going to form an equation. Before I start using the equation, we're going to introduce a new letter. So this letter that I'm drawing, that letter is the lower case Greek lambda. Lambda. That's the name of the letter. And we just call it lambda. There's a capital lambda and there is a lowercase lambda. So there is the lambda. And there's a system of equations we're going to form. Those two have to be parallel. In order for two vectors to be parallel, one has to be a factor of the other, a scalar factor of the other. In other words, one could be 2 times the other, or 1/2 the other, or a third of the other, some kind of fraction or multiple of the other. So 1, 2 should be some constant times the other, 2x, 2y. And we want to preserve this restriction though, because just solving this equation is going to give us multiple solutions, you know, one here, one there. As the circle keeps growing, we're going to get multiple solutions, but we want to stay with the x squared plus y squared equals 25. We don't want to be with x squared plus y squared equals 36, for example, or 26 or 14 or whichever number. We want to stay with 25. So x squared plus y squared equals 25. So this is the system of equations we want to solve. Let's break this up. This means that 1 is equal to 2x lambda or 2 lambda x. 1 equals 2 lambda x. And 2 is equal to 2 lambda y. 2 lambda y. If two vectors are equal, that means the corresponding components have to be equal, which means this has to be equal to that, except that we have to multiply by lambda first. And the second component has to be equal to the second component, except that lambda should be also included. And we got to keep this, x squared plus y squared equals 25. So initially, when we compare the vectors, we have only 2 equations. But then when we break down the equations into components, we end up, in this case, with 3 equations. So this is the system of equations we are about to solve. Yep. So system of equations. So all of these problems in this video are going to boil down to a system of equations that we have to solve. We have 3 equations and 3 unknowns. What are the unknowns? X, y, lambda. And then after that, we're going to use whatever we obtain from that system of equations to figure out which one the maximum is or the minimum is. Yeah. All right. Whenever you are solving a system of equations, the very first thing we want to make sure we do is clear up the zeros. Are the zeros part of the solutions or not? Is 0 going to be involved at all? The reason is because eventually you want to be able to divide by the variables, and we cannot divide by 0. So we have to exclude 0. If we divide by the variables, we are inadvertently assuming that the variable will not be 0. So we have to make sure we know whether the variable will be 0 or won't be 0. Now, so we start analyzing the system of equations. Yeah, every system of equations may be different than the previous system of equations. It's just a different animal, and you have to analyze it one by one. There's no system. Well, there's somewhat some systematic rules like the zeros, but after that, just about anything goes. Anything that is algebraically correct goes. So, so if I apply one method here, that method may not work as smoothly on the next example, and that's the nature of math problems of this caliber, of this level. Every problem could be different. What you learned in one is not going to necessarily going to be applied completely on the second problem. The general method, the setup is the same. So this is the setup. The setup is the same. But, and then this is the second setup, I suppose. So those are two ways of writing the setup. This is the one we're going to work on. So the setup is correct, but how do we go about solving the system? That varies from problem, varies widely from problem to problem. Anyway, so let's talk about zeros. Can x be zero? And the answer is absolutely not. In this case, it may in some cases, but not in this case. Why not? Because if x was zero, that would cause this product to be zero, and zero cannot be equal to one. So x cannot be zero. Can y be zero? No, because again, if y was zero, then this product would be zero, and zero is not equal to 2. So y cannot be zero. Yep. Can lambda be zero? No, because if lambda is zero, was zero, then again, 1 would be equal to 0. So none of the variables involved may be 0, and that is good. That means that we can divide um, by any of the variables because none of them is going to be 0. So so that is the very first thing you want to do whenever you are solving a system of equations. This is a nonlinear system. It is we cannot use matrices or elimination, yes, but we have to be very careful with elimination. All right. So first, I look at the second equation. And of course, we can divide by 2 to simplify. So 1 equals lambda y. There are many ways to go about this. I would say a lot of people would solve for lambda, rather for x and y. And then we will have a lambda hanging in there. And then we substitute those in here, and that will for sure work. I'm going to use a different method. So take this equation, the first equation, and multiply by y. So y is equal to, multiply that by y, and then we have 2 lambda yx, 2 lambda yx. So I'm just taking this equation, multiplying by lambda. And the reason for that is because lambda y up here says is equal to 1. So this guy is equal to 1. See, lambda y equals 1. So that is the same thing as 2 times 1 times x, or 2x. So we just established that y is double x. Okay. Let me continue on a new page. So, and let me copy the system of equations and then on the new page. So we had 1 equals 2 lambda x. 1 is equal to lambda y. You got to be careful with the lambdas because if writing the lambdas, because if you extend this line a little bit and you cross the longer stick, the longer line, then that may look like an x. So you got to start writing your equations carefully. X squared plus y squared equals 25. Notice that I did simplify the second equation by dividing by 2 both sides of that equation. And then we have a new equation that came from that. Let me write down that we did not have zeros. X cannot be 0, neither can y be 0, nor lambda can be 0. Okay. And we have a new equation. There it is, y equals 2x, y equals 2x. Okay, so we can substitute this equation in here. So x squared plus 2x quantity squared equals 25. So we have a single equation um, on x. So that is 1x. That is going to end up being 4x squared after we square that. So 1x squared plus 4x squared is going to be 5x squared. So those two together are going to be 5x squared. We can divide by 5. So x squared is going to be equal to 5, which means that x equals plus or minus the square root of 5. Yep. So if x squared is 5, yeah, back here, if x squared is 5, we can plug that into that equation again, and that's going to give us 5 plus y squared equals 25, which means that y squared is 20. And so y equals plus minus 2 times the square root of 5. And that, of course, you know well that that came from the square root of 20. When we simplify the square root of 20, we end up with square root of 4 times 5. The 4 pops out of the root. So we end up with 2 square root of 5. So lambda, lambda is the reciprocal of y, according to this. Yep. So let's, at this point, what I like to do is organize what we have on a table. So we're going to have x, y, lambda, and the output of the function. So we have square root of 5 for x. For y, we will have, we got to be careful here. So yeah, we got to analyze what's going on. You have to pay attention to what is going on, to everything. So here we have a positive and a negative x. Here we have a positive and a negative y. When you combine those, you can have 4 scenarios. You can have positive, 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 negative, negative, positive, negative, negative. So you can have 4 scenarios, all the different combinations initially. And we should start considering four of them. Square root of 5, negatives, well, square root of 5, 2 times square root of 5. Negative, positive, positive, negative, negative, positive. If all we knew were those 2, then we would end up with 4 combinations. However, see, everything has to be considered. However, y equals 2x. So that tells us that x and y have to have the same sign. If x is positive, if you multiply by 2, you're going to end up with a positive number. So y has to be twice that. And if x is negative, then y has to be twice that. Yeah, y is twice x. So we don't have 4 possibilities. But again, we have to take everything into consideration. We cannot just look at those 2, because if all we do is look at those 2, then I have 4 possible combinations. And we don't necessarily know that the positive goes with the positive and the negative goes with the negative. We don't know that in advance unless we have some other piece of information that tells us that that is the way it's going to happen. Otherwise, we wouldn't know necessarily. The lambda, based on this equation, is going to be 1 over the y value. So 1 over 2 times square root of 5 and negative 1 over 2 times the square root of 5. Okay. When you're writing your answers, when you're writing your work for the assessments, please have a table. The table will be part of the answer, not the final conclusion, but that is going to be part of the answer. That is part of what I'm going to be assessing, as well as your work. All right. And then the output. Let's go back to what the function was. The function was x plus 2y's. So if we add this plus 2 of those, we're going to end up with 5 square root of 5. If you add that plus 2 of those, we're going to end up with negative 5 square root of 5. And now you observe those and see which one is the biggest and which one the smallest is. The biggest is this, the smallest is that. So that is the maximum, and that is the minimum. Back here, we didn't know. I told you you could have done x squared plus y squared minus 25, or you could have done 25 equals x, rather, or 25 minus x squared minus y squared. You could do that. The only difference with that is that the lambdas, I think, will be different. They would be opposite. I have to actually do the problem. But at the end, you're going to end up with the same inputs, and we're going to end up with the correct outputs corresponding to those inputs. So the only difference is that the lambda will be different. The more I think about it, I think that's what it will happen. If you reverse the g, if you do the opposite, again, the only difference I believe is that the lambdas are going to be opposites of what we find. But we're not using that. We're not using the fact that this is positive or negative. We're using those outputs to determine which one the maximum is and which one the minimum. And of course, the one that is biggest is going to be the maximum. So this is the table that you have to include. This is just a table. But we still have to give a solution. So f achieves maximum. Forgive me, I don't want to look up how to spell correctly. Achieves maximum of 5 square root of 5 at square root of 5, comma, 2 times square root of 5. F attains, there, I know how to spell that well, minimum of negative 5 square root of 5, and it's an absolute minimum, well, under the restriction, at 2 negatives, negative square root of 5, comma, negative 2 times square root of 5. Yep, so that is the conclusion. This is the final answer. But you have to back it up with all the work. You have to show all the work when you're writing all of this. Yep. And back in the picture, it does make sense that if you have an inclined plane, the maximum is going to be at one end and the minimum will be exactly on the opposite end. When you write your answers, try to make sure that the points you're providing actually belong to the restriction. If you square this, you get 5. If you square that, you get 20. 5 plus 20 is 25, which is the restriction we had. We want to optimize this subject to this restriction. So the inputs have to fulfill the requirements. Let's do a second example. Example 2. Okay. F is going to be, and it's an f of x and y, x squared plus y squared minus 2xy. And we're going to subject this to an ellipse. So we're going to have an x squared plus y squared over 4 equals 1, which is an ellipse. We did this, we analyzed this a little bit in a previous video, this function. If you go down this diagonal, the 45 diagonal between the x-axis and the y-axis, then we have parabolas opening up. So this is kind of like, it's like a hard shell taco, if you will. Yeah, and opening up on this diagonal. And then so that is the surface. We want to find the maximum. Now, without restriction, this has no maximum because this keeps going up. It's a parabolic in a way. Well, it's a cylindrical parabolic, except that usually a cylinder is straight relative to one of the main axes. This is straight relative to a diagonal. So I don't know if we would call this a cylinder. It is a cylinder in the sense that if you go in one direction, you end up with the same problem no matter what. So I guess it could be a rotated cylinder. Be as it may. Um, oh, maximum. I want to maximize and I want to minimize subject to this. Now this is an ellipse. Um, the axis, so it opens, it goes up to 2 on the y. Whoa, so this is an ellipse like this. So within this input, where's the maximum? Where's the minimum? I know there's going to be a minimum here and on the opposite end, because these are parabolas that go up. So I know this is going to touch the floor, but then this is going to go up somewhere and we're going to find maximums. And that's what we want to figure out, what the maximums of this cylinder is, this F, subject to this restriction. And we're going to be just on that boundary, nowhere else but that boundary. Yeah. Yeah. There is a second way of doing this now that I think of it. We're going to go back to example 1 and do it in a more primitive. We can redo example 1 in a primitive way without Lagrange multipliers. Yeah. So let's start. F, the gradient of F is going to be 2x minus the derivative of that with respect to x, which is going to be 2y, comma 2y minus 2x. G, well, I haven't said what G is, so let's say what G is. G is equal to this guy, x squared plus y squared over 4 minus 1. So just take everything to one side of the equation and make that expression a new function G. The gradient in G will be 2x, comma, 2y, but then we got to divide by 4. So it's really y over 2. Okay. And the setup is that the gradient F equals some constant, the gradient G, plus the restriction itself. And x squared plus y squared over 4 equals 1. So this is the initial setup. Yeah. Setup. Because, again, this is going to increase. See, this is more complex. This is not a plane. This is, example 1 was a plane. So all the vectors were going in one direction of increase. But here, the vectors are not necessarily going to go in one direction. They're going to go in perhaps different directions of increase. So it's not as simple anymore as the example 1. This can be translated as, well, the gradient of F is 2x minus 2y, comma, 2y minus 2x equals constant times 2x, comma, and y over 2. I'm simplifying the 2 and the 4. And then I don't have enough room to put the restriction. X squared plus y squared over 4 equals 1. So that's another way to write the same setup. So that is a setup. Okay. But the way we want to write it is by actually breaking this up into coordinates. So this coordinate should match this coordinate, except that the lambda should be included in that. So 2x minus 2y equals 2 lambda x. And that second coordinate, 2y minus 2x, should equal y over 2 times lambda. So lambda y divided by 2. Yep. And then we have this restriction, x squared plus y squared over 4 equals 1. So this is the system of equations that came from the setup system of equations. And what we want to do is solve the system of equations, tabulate all the information we obtained on a table, put it on a table, and then from the table we can figure out maximums and minimums. So this part is relatively easy. The work really starts here as we attempt to solve this system of equations. Um, what is the first thing you do when you try to solve a system of equations that is nonlinear? And these are nonlinear systems of equations. And that is and besides we're multiplying the lambda with the x, so that already makes it nonlinear. Um, the first thing we want to do is look at zeros. Could x be 0? Yes. If x is 0, what are the consequences of x being 0? So let's go to the ultimate consequences of one of the variables being equal to 0. Can x be 0? The answer is yes. If x is 0, this whole thing becomes 0, and so does this. And so negative to y is 0, and that forces y to be 0. But if x is 0 and y is 0, that forces, well, if x is 0, then y has to be 0. And those two may not add up to 1. So that implies that 0 is equal to 1, which is a contradiction. The symbol for contradiction is two arrows crashing against each other. So we cannot have x equal to 0. X may not be 0. Initially, it looks like it was going to work out, but x equals 0 forces y to be 0, which forces those two to be 0, or 0 equaling 1, and that cannot happen. Okay, good. So we established that x cannot be 0 because when you take that to its ultimate consequences, we end up with a contradiction. That means that the premise of x being 0 may not happen. Can y be 0? So let's put an if here. If x is 0, if y is 0, what are the consequences of that? If y is 0, there's y. Okay. If y is 0, regardless of the value of lambda, this product becomes 0. This becomes 0. So that forces x to be 0. And that when you plug in that y of 0 and that forced x of 0, we end up with, again, 0 equals 1. That is a contradiction. After the contradiction, we can establish, so x may not be 0. And likewise, so y may not be 0, not 0. Okay, can lambda be 0? Okay, so first we establish those two. If lambda is equal to 0, let's see, 0, that forces x to be equal to y in both cases, because then we have a 0 here. So 2x minus 2y would be 0, divide by 2, and the x equals y. Then x equals y. And at that point, we don't perceive any contradiction. So there's no conclusion. Other than that, there's no further conclusion yet. So we're not saying it cannot happen. We are not saying it may happen. We don't perceive any contradiction yet. See, as a scientist, we don't know things until we have information or evidence about what we are analyzing. Otherwise, we always have an open mind. We just don't know. And it's not a matter of wishy-washy. We just don't know. Okay, so let me copy the system of equations again on a new sheet. We can simplify the 2 now that I look at that. So x minus y equals lambda x. We can multiply by 4, rather by 2. So 4y minus 4x. 4y minus 4x equals lambda y. And we can multiply that equation by 4. I just want to double check that I multiply this 4. Yep. and then multiply this by 4. So we have 4x squared plus y squared equals 4. So there's our system of equations. I just rewrote it. We have one conclusion: x may not be 0 and y may never be 0, because those two get us into problems, get us into contradictions. So now the question, so we still have to solve this system of equations. Um, I'm trying to think how to solve this. Okay, lambda may be 0. We did not quite finish that. If lambda is equal to 0, because it seems that it would be nice if I could divide by lambda at some point. You know, I was thinking of eliminating those. Those are the same, similar. They're not the same, but we can multiply by -4 here, and then we can simplify those two. But then we will end up with something with lambdas, and then getting rid of the lambdas may not be as easy. Because we may not divide by lambda, because if we divide by lambda, we are assuming that lambda cannot be 0. But we haven't finished this case. So we have to go by cases, and we're using 0 as a pivotal point of going down the cases. If lambda is equal to 0, that means that x is equal to y. So let's move on here. Then x is equal to y. And that means we can solve this equation for x. Because if they're equal, if x is equal to y, if x is equal to y, that means that this is x squared, or we can rewrite this as x squared. So we have 4x squared plus x squared, assuming they are equal, equals 4. So that is 5x squared equals 4. So 5x squared equals 4, which means that x equals, if we divide by 5 and take the square root on both sides of the equation, we end up with positive negative 2, because we're going to be taking the square root over square root of 5. Okay. And y will be identically equal. Okay. So those are the consequences. We found what x would be and what y would be if lambda is equal to 0. Okay, so that is taken care of. Okay, if lambda is equal to 0, x would be this number, y would be the same. Or x could be the negative of this number, and y would be the same. So we went through the consequences of lambda equal to 0. That case is dealt with. Now, we're going to deal with the case when lambda is not 0. Okay. Always pay attention to the zeros. The zeros could be your friends or your biggest enemies, because they're going to sneak out. It's kind of like that. The zeros are going to, they're going to walk away, and you're not even going to notice. So you got to pay close attention to the zeros. And the reason for that is because we can inadvertently divide by a 0, and that causes the 0 to go away. Anyway, so if this is the case, we can multiply the first equation by -4. So multiply by -4. And that's going to give us -4x. -4x plus 4y equals -4 lambda x. I'm going to rewrite this equation again differently. -4x. I guess I could have just multiplied by 4, but that's all right, because we're going to subtract now. But -4x plus 4y equals lambda y. So we subtract this equation minus that equation. Those two are going to be 0. So 0 will be lambda y plus, boy, that is confusing, 4 lambda x. Yep. Let me double check to make sure I didn't mess this up. X, Y. If we were to add it, yeah, I think that we're good. So, so lambda y is equal to negative 4 lambda x. Divide by lambda. So y equals negative 4x. See, the reason why we were able to divide by lambda is because we're in the case, the scenario where lambda is not 0, so dividing is not a problem. And we have a completely different relationship than here. Here we have the relationship that x equals y. Here we have the relationship that x is not equal to y. Well, no, it is y is negative 4. They have opposite signs to start with, and one is 4 times as much as the other. Okay, now we use this equation. We substitute this y into that equation, into this restriction. So 4x squared, thus 4x squared plus y squared, but that is the same thing as negative 4x quantity squared. 4x squared plus negative 4 equals 4. Yep. So 4x squared plus 16x squared equals 4, which means 20x squared equals 4. So divide by 20, simplify the 4s, we end up with x squared equals 1 over 5. Again, 4 plus 16 is 20, x squared. Divide by the 20, 4 divided by 20 is 1/5. Yep. And then we take the square root. So x is plus or minus 1 over the square root of 5. And the y is going to be the opposite. Where is it? There it is. Y is going to be the opposite of x multiplied by 4. Okay. So now let's start putting together our table. I'm going to try to squeeze it in here. No. Let's do a new page. It's not good to squeeze sometimes because there's a lot of information we have to put together here. So our table will contain x column, y column, lambda column, f column. Okay, so in this case, when lambda is equal to 0, we have 2 over the square root of 5. Y has to be equal to 2 over the square root of 5. By the way, without this, if I only had x equaling this and y equaling plus minus, then I wouldn't know which plus goes with each plus or which minus. We would have to consider all 4 possibilities: plus, minus, minus, plus, 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 minus, minus, all the 4 possibilities. But this equation tells us that they have to be the same sign. Negative 2 over square root of 5, negative 2 over square root of 5. Lambda is 0. Here, we also get values. X could be 1 over the square root of 5 instead of 2 over the square root of 5, 1 over the square root of 5. Y has to be opposite and 4 times as much. So if x is positive 1 of that, y has to be opposite and 4 times as much. If we have negative 1 over the square root of 5 for x, y has to be opposite of this number, so 1 over square root of 5, 4 times as much, 4 over square root of 5. The lambda disappeared in this because we did divide by lambda. So we have to recoup the lambda. We divided by lambda, but we never, so how can I get the lambda back? What is the value of lambda? And I'm going to ask you to find the lambda. The lambda is the multiplier, the Lagrange multiplier. Where did the lambda? Oh, If you do x minus y back here, you get twice x. No, the lambda x. Okay, so we can substitute, since we already know x and y through this process, we can substitute here. So if x, let's start with this guy. If x is 1 over the square root of 5, 1 over the square root of 5, y is opposite 4 times as much, and that is equal to lambda x, 1 over the square root of 5. Okay, so that is 1 of those plus 4 of the same, that's 5 over the square root of 5 equals lambda times 1 over the square root of 5. We can multiply square root of 5 up here. So we cancel multiply by square root of 5. So lambda has to be 5. So when x is 1 over the square root of 5, lambda is just 5. It's a nice whole number. Let's make sure the lambda is, so if we start with, so if I'm using this equation to figure out the lambda. If x is negative, 1 over the square root of 5, took away the y, which is, remember, opposite of, this is a negative. The opposite would be positive, 4 times as much. And that is lambda times the x value, which is negative, over the square root of 5. So there's a parenthesis that closes out here. And this is not a fraction. This is just a line that divides this with that. So we have a negative 5 over square root of 5 equals negative lambda over the square root of 5. So again, lambda is equal to 5. Okay. So we got this row, this row, this row, this row. Now let's figure out the output of the function. That was on one of the previous pages. Remember the function. The function is square the first one, square the second coordinate, took away twice first and the second coordinate. Okay. Well, if they're the same, squaring it is going to give us 4 over 5 plus 4 over 5 minus twice 4 over 5. So the output of the function is going to be 0. You can actually plug them in and realize we get 0. This is going to be the same because we're squaring. The two negatives cancel each other out. The two negatives when we multiply x with y. So we end up with 0. That was expected because on the picture here, on this picture, we did see that if we go on the main diagonal, we're going to hit 0. So this 0 corresponds to 2 over the square root of 5, 2 over the square root of 5. The 0 back there corresponds to those two opposite, diagonally opposite, which makes sense. And then we're going to have a maximum and a maximum there. Okay, so we got to be more careful with this because those are not going to be zeros. So this is going to be 1 over 5 plus, I better figure this out. So 1 over 5 when we square this plus 16 over 5. And then we're going to take away 2, multiplying those two together. Okay, so one of them is negative. So that means this negative and that negative are going to make a plus. Multiplying those two together, we're going to end up with 4 over 5 because 1 times 4 is 4. Root and root is just a 5. So 4 over 5, we already took care of the negative with the plus, but then we got to double that. So that is 8 over 5. So 8 and 16, 24, 25 over 5. So the output is going to be 5. That is a coincidence. And then the same thing will happen on the other one because when we square the x, the negative vanishes just as this negative vanishes when we square the y. And then when we multiply those together, with one of them is positive, the other one is negative. So we end up with one negative plus this negative, that makes it a plus. So the output is 5. So back in this picture, yep, we end up, this point up is going to go up to 5, and so is this one going to go up to 5. So this is the table. You have to show your table. And the conclusion is that a f has a maximum of 5 at, so this is the maximum, and then we have to write the coordinates. We can factor out the 1 over the square root of 5 out of the vector 1 comma negative 4 and 1 over the square root of 5 negative 1 4 negative 1 4. So those are the 2 points where we have a maximum. So that we can write this as a bullet. Second bullet, f has a minimum of 0. That's the output 0. That's, I haven't analyzed in more detail, but that is very coincidental. Typically, let's look at example 1. The lambdas and the outputs are not quite that related. Yeah, I mean, here in example 1, the lambda and the outputs are not, I mean, they do both possess square root of 5, but they're not the same answer. So that is just a coincidence that we got here. We have a minimum of 0 at, we can factor out the square root of 5, 1 over the square root of 5, and then we have 1 negative 4. I wrote it wrong. I'm going to fix that in a moment. 1 negative 4, because those cannot be the same. Not in this case. Square root of 5, negative 1 4. Yeah, we can factor out 2 square root of 5. I'm going to fix this. 2 square root of 5, and then just have, sorry about this again, 1 1. So 1 1, factor out 2 square root of 5. Factor out the 2 square root of 5, 2 over the square root of 5, and then we have negative 1, negative 1. That's embarrassing, but it's good to fix it right now. Yeah, I should have known that when I was showing you the picture, because we have 0 in the main diagonal, so it doesn't make sense to go off the main diagonal. The main diagonal is 1 1 or negative 1 negative 1 on the x and y axis, x and y plane. So, and this is off, so you go 1 negative 4. If we continue here, 1 negative 4, and that's where we end up with the maximum. So this is, it gets a little bit, not exactly, but it's a weird picture to show. Yeah, kind of like this. It's kind of like a hard shell tortilla, and you get the minimums here and the maximums there. Yeah, and things are not totally symmetric because the restriction was not a circle, it was an ellipse. Yep. Just want to double check one more thing before I call this good. I want to make sure that this actually fulfills, these points fulfill the requirements of the restriction. Okay, so 7. The points that we found, oh yeah, they are. I just realized they are, because I was thinking, well, 1 squared, and then this doesn't quite work, but I forgot that we have those roots. So yeah, things will work out okay. Let's move on to, and if not, please let me know. An example in 3 variables. So this is going to be example 3. We're going to maximize or minimize f. F is going to be a function of 3 variables, x, y, z. And we're going to keep this simple, x plus 2y plus 3z. So 3 different coefficients, just to keep them separate. Under the restriction, subject to x squared plus y squared plus z squared equals the unit circle, the unit sphere rather. So within that sphere, we're going to have a unit sphere, and we're going to only take into account points on that sphere. In that sphere, there's going to be one point at which, when we plug in the coordinates of that point, 1x, 2 of the y's, and 3 of the z's, we're going to end up with a maximum. Yep. And we're going to end up with a minimum, which is probably going to be diagonal to the sphere based on this kind of function. So the initial setup, remember, nabla f is equal to lambda g, or rather nabla g, there you go. See, the gradient of g should be parallel. This equation establishes that they have to be parallel. The gradient of f has to be parallel to the gradient of g, and the constant lambda is the one that causes that to be the case. And we have to have this restriction, x squared plus y squared plus z squared equals 1. All right, so this is the initial setup. Although we did not say what g is, it is understood that it is going to be this minus that. So the gradient of f is 1, 2, 3 equals lambda. And I'm not going to write down g, but g is x squared plus y squared plus z squared minus 1. And the corresponding gradient will be 2x, 2y, 2z. Yep. And the restriction x squared plus y squared plus z squared equals 1. So there's the, you know what, we should write g. Set g of x, y, z. I don't want to be too slappy, x squared plus y squared plus, or too informal, z squared minus 1. Yep. There. So that's how we get the corresponding gradient. Okay, so that causes us to have a system of equations. 1 equals 2 lambda x, 2 lambda x, 2 is equal to 2 lambda y, 3 is equal to 2 lambda z, and x squared plus y squared plus z squared equals 1. So this is our system of equations. So lambda, rather x, is 1 over, oh, wait a minute. I almost forgot my rule. How about the zeros? Zeros. What about the zeros? Can x be 0? So there's an if before that. If x is equal to 0, if x is equal to 0, this product is equal to 0, so we end up with 0 equals 1 or 1 equals 0. Then 1 is equal to 0, which is a contradiction. This is the symbol for contradiction. It's two arrows crashing against each other. So no, it cannot be 0. And likewise, y cannot be 0, neither can z. Can lambda be 0? No, because then if lambda is 0, we have the same thing. Then 1 is equal to 0. So yeah, so none of the involved variables may be 0 at all, because we have a complete contradiction. Good. That means that we can divide, because the next thing I was going to do is divide by 2 lambda. Yeah, you always got to be careful when you divide. Divide is tricky. X is 1 over 2 lambda. Y is 2 over 2 lambda. And z, there's a comma in between, z equals 3 over 2 lambda. So now we can plug those 3 in here. A lot of students do that, which is what I'm going to do. 1 over 2 lambda squared plus 2 over 2 lambda squared. You could think, well, why don't we simplify? Because we want to keep things consistent. We could, but then this way we have the same denominator no matter what. So we have 1 squared plus 2 squared plus 3 squared is the same as 1 plus 4 plus 9. 1 plus 4 is 5, plus 9 is 14. So we end up with 14 over 4 lambda equals 1. Oh, 4 lambda squared. There we go. Okay, so 14 over 4 lambda squared equals 1. Okay, let me write that down on the next page. So 14 over 4 lambda squared equals 1, which means 1 over 4 lambda squared equals 1 over 14, which means that if we take the square root on both sides of the equation, 1 over 2 lambda is equal to plus or minus 1 over the square root of 14. And you may be asking, wait, why didn't he just solve for lambda? The reason is because I'm looking at the x. I'm looking ahead. X is 1 over 2 lambda. So this is automatically x. Yeah. And whatever x is, lambda, y rather, whatever x is, y is going to be twice as much based on those two equations. See, this is x, this is y, twice as much, and z is going to be 3 times as much. So instead of looking for lambda, I'm thinking of chess. In chess, you know, you can capture a whole bunch of pieces, but what matters ultimately is whether you have a checkmate. So that is like the checkmate, the x, y, and z, although we still want to get lambda. Anyway, so let's start putting together our table. I think we are ready to start. So we have a column for the x's, a column for the y's, a column for the z's, a column for the lambdas, and a column for the function. Whoa, we got a bunch of columns now. In comparing to the last example, we had 1, 2, 3, 4, 5. We had 4 columns instead, the x, the y, no z, still lambda, and still function. Okay, so the x is, oh, it is up here. It is 1 over 2 lambda. 1 over 2 lambda is plus or minus. So let's take the plus for now, 1 over square root of 14. Y is going to be twice as much. Z is going to be 3 times as the original x. If we have a negative 1 over the square root of 14, then the y is going to be twice as much, negative 2 over the square root of 14, and the z is going to be 3 times as much. And we're not going to have combinations because we're solving for 1 over 2 lambda, and x, y, and z is 1 over 2 lambda times 1, 2, or 3. So they're fixed. The lambda, well, I guess we can solve now for lambda, so we can multiply. I'm going to do it over here. I'm going to end up multiplying by lambda anyway, or obtaining lambda. So cross multiplication, so that means that, now I got to be careful. Let's stick with the positive one. That way the lambda will be the same, will be positive. Because if lambda was negative, then we would have to pick the negative. Okay. So cross multiply, and 2 lambda equals plus or minus the square root of 14. But we got to be careful which one stays with which. Lambda equals square root of 14 over 2 plus or minus. So this is square root of 14 over 2, square root of 14 over 2. And the output remember what the original function was. The original function was x, 1x, 2y's, and 3z's added together. 1x and 2y's and 3z's. So that is 1 and 2 of those make 5 altogether. And 3 of those, that's 9, so that's 14. Oh, so that is really 14 over the square root of 14, which is just the square root of 14. Same thing over here, but all of them negative. So the output is negative square root of 14. Okay, so there is the table. Remember, table is part of your answer. And then we end up with the final solution, or the conclusion. Conclusion is that f has max of square root of 14 precisely and exactly at the point 1. I'm going to factor out 1 over the square root of 14. So we can put, so this is a scalar times the vector 1, 2, 3. If we factor 1 over the square root of 14, we get that. And f has minimum, or attains a minimum, of negative square root of 14 at, we're going to factor 1 over the square root of 14. We could factor the negative, but I want to emphasize, excuse me, that it is exactly on the opposite direction of the sphere. So this point, including this vector belongs to the sphere. And so this one, and they're on opposite sides of the sphere. And notice that there's no symmetry in the sense that, well, there's symmetry with respect to those two. Those two are diagonally opposite to one another, but it's not at a 45-degree angle. Who knows what the angle is on the first octant? All we know is that this is on the first octant of the sphere, but we don't know the precise angle. I mean, we can compute it. That doesn't take too much, but yeah, that is one of the solutions. That's where the sphere, the point of the sphere, will have the maximum f value, and the f value will be square root of 14. Once you give the conclusion, the lambda is gone. The lambda is only there for purposes of showing the work and making sure everything works well. Before we leave, I just want to ask a question. Remember the first page, we did 2 examples like this. So 2 examples. We did 1 example like that, 1 example. And what about this guy? This is a weird one. I want to live with an example. I want to leave you with an example of that, which I have to admit, it is a weird thing to ask for. But I want you to think about it, please. And don't do it necessarily with Lagrange multipliers. I haven't thought about Lagrange multipliers, but don't do it with Lagrange multipliers. Just think about the example. So this is just a weird example to think about. This is example 4 in a test or a quiz. I'm not going to ask you for an example 4. Well, I don't know. Anyway, so take just a generic function, f of x equals a simple one. So optimize, and that means maximize and minimize. So find the maximum subject to, and then I got to give you an equation that has x in it. So I just think of, okay, x minus random number 5, x, I don't know, plus 6 equal to 0. So this is the equation, and this is the function. So optimize this and minimize this. So as in the previous conclusions, what is after you do all your thinking, the conclusion should be f has a maximum blank at x equals blank. F has a minimum of blank at x equals blank. That should be the conclusion. of this maximizing or minimizing subject to this restriction. It's not that hard once you know what you're thinking about, but it can be confusing when you relate this to Lagrange multipliers. With this, we stop this video.